Hello, everybody. So today we're going to go from the qualitative description of chemical elements to actually trying to describe how much matter is present in a sample. So we're going to be doing this mostly by talking about, well, how we can count atoms. So one of the first important things to realize is that when I've been talking about the history of science, one of the impressive bits is most of what we've been talking about so far was done originally just using the mass of various chemical elements, because you can determine the mass of each element present in a sample. Now, this ends up being slightly problematic because if we go back to Dalton's use of definite proportions, all of this was just done using mass ratios and not molar ratios. And you can kind of see why this gets a little bit messy if we look at, say, carbon dioxide, because the ratio of oxygen to carbon, the mass ratio of oxygen to carbon in CO2 is 2.66 to 1. That's a really kind of messy number. However, if we're able to go to atomic ratios, well, this is a lot easier. This is just a 2 to 1 ratio. However, and this is also kind of further emphasized by the fact that, well, even if I go from mass to atomic ratios, it turns out that it's often inconvenient to try and count those individual atoms because, well, it turns out there's a lot of them there. And one of the reasons why is because if I'm looking at single carbon atoms, each one of them weighs about 2 times 10 to the negative 23rd grams. This is also 20 yoctograms, which I think is just a fun word to say, yoctogram. So we need to find a more convenient way to try and count our atoms than mass or atoms. So for that, we're going to go ahead and look at moles. Not this kind of mole, definitely not that kind of mole. We're going to make him go away. He's a little scary. So a mole is essentially just a way of counting a very small object. So the way I like thinking about it is if I'm looking at a dozen things, that's 12 objects. If I look at a gross, that's 144 objects, also known as a dozen dozen. A mole is just similar, is a very similar thing. The only difference is it's about 6 times 10 to the negative 23rd objects. So a whole lot more. And one of the important things is that you can actually apply moles to anything, be them atoms, be them molecules, anything you want. And so we're often going to refer to this conversion in between objects to moles as Avogadro's number. So Avogadro's number is just equal to that many number of objects per mole. And it can be used to convert any number of properties. Two major types of ratios we're often going to deal with are going to be the number of moles of a given atom. So there, for 1 mole of carbon, there's 6 times 10 to the 23rd carbon atoms. The other major ratio is moles of a molecule, or number of molecules in 1 mole of a molecule. But again, doesn't really matter what you use, whether atoms, molecules, or again, even moles. Worth noting that it turns out that a mole of moles would be about the size of the moon. And in order to describe it, you actually have to involve planetary tectonics. If you're interested, go ahead and follow this link. It's kind of fun. However, when we're looking at chemical systems, typical good way to think about it is a mole of carbon atoms weighs about 12.011 grams. This is actually the definition of a mole of carbon. This is how we get this number. So what this allows us to do is convert directly from mass to moles using our molecular weights. So we're going to try and be doing this conversion of mass to moles of any given element. So in order to do this, we need to find the mass of each element per mole. So this is where the atomic weight comes into play. So we've worked with atomic weight and atomic mass units. Well, it turns out these AMUs are also related to the grams per mole and not just the weight per atom. So there's a very strong correlation in between these. So you're often going to find your atomic weights instead of reported in AMU as grams per mole or in the abbreviated grams per MOL. They're pretty much the same thing. It turns out we can use these conversions for molecules. And when we do, instead of talking about atomic weight, we're often talking about molecular weight and molar mass. They're all essentially referring to the same thing, which is the weight of an object per mole. So if I'm going to look at, say, the molecular weights of carbon, this is again defined as 1 mole of carbon 12 would weigh about 12 grams. And again, we can use this to figure out 1 gram is about the same as about 6 times 10 to the negative 23rd AMU. So it's a fairly kind of fun conversion there. Sorry, that'd be 6 times 10 to the 23rd. I'll remove the negative when I post the slides. So we can use these atomic weights to try and determine molecular weights as long as we know our chemical formulas. And we're going to dive into this a little bit more in the next chapter as we talk about more about molecules. But let's go ahead and look at this idea of CO2. So this molecule contains 1 carbon atom and 2 oxygen atoms. So we can use this to determine the mass of 1 mole of CO2. So if I have 1 mole of CO2, this means I've got 1 mole of carbon, and each mole of carbon weighs 12 grams. So 1 mole of CO2 has 12 grams of carbon. We can repeat the same process for oxygen and find out it contains about 32 grams of oxygen. We can then combine this and say for 1 mole of CO2, 12 grams of carbon, 32 grams of oxygen, total mass of 44 grams. So this is actually a fairly useful way of working with moles. As soon as you know atoms, you know molecules. And this is a really powerful feature. It's also going to be possible for us to use using mass ratios, such as as you're able to determine with Dalton's law, turning those into those molar or atomic ratios of atoms. So let's go ahead and look at, say, CO2. So for CO2, if I have 1 gram of carbon, well, each gram for each mole of carbon has 12 grams of carbon. So I'll set it up to can't make the grams cancel. Then I can convert from moles of carbon to moles of oxygen, and then from moles of oxygen to grams of oxygen. So this is one way I can confirm, based solely on the molecular formula, the mass ratio of grams of carbon to grams of oxygen. And this actually just kind of gives us a taste of the big power of moles. So whenever you've got a big chemical problem and you're trying to do unit conversions, a general good idea is to always convert to moles first. So when in doubt, mole it out. And this is going to be some features that we're going to use a little bit more in detail as we kind of revisit Dalton's law of proportions next time when we're looking at percent compositions of real chemical samples. So this gives us a way of looking at essentially how we can determine molecular compositions of species. Until then, take care.